Mic check. I think it's good. Good morning. Last meeting, everybody. So hopefully our meeting today will sort of just help you feel like you're cruising to a good finish in the class. I'll get to grading the second projects as fast as I can. So if you manage to complete it, or at least get something submitted, then hopefully that felt good, because that was not an easy project. It's not an easy project, the culmination of this entire semester. Okay, good. Glad to hear it. Good morning, Tyler. Got a check on the mic. So anyway, we're kind of into, I wouldn't call this bonus content, but of course you had your last project already, so there's one more lab, one more discussion, one more homework, and then you're done. But I think sort of at least understanding the major point of today's lecture can be useful. So we're talking about how do you actually represent floating point numbers in binary. And this is very valuable because it helps you understand, in my opinion at least, it should help you understand better why floating point numbers are so difficult in programming. If you didn't know that, by the way, floating point numbers are very difficult to deal with in programming. And it's entirely because of the way that computers store those values. So we'll do a couple of examples. You don't have to do any of the handwritten work. You can just watch me do it. But what I want you to walk away with is an understanding of, oh, floating point numbers are terrible for programming. They're very difficult because they're so uncertain. Probably you're all too young for this, but if you've never watched the movie Office Space, there is a sort of an indirect reference to what we're talking about today. So in Office Space, they talk about stealing money from a bank because of these leftover tiny little pieces of floating point values. And that hack on the uncertainty of floating point numbers was actually first presented in the movie Superman 3, so they also reference that in Office Space. But anyway, the whole point is that in the movie, at least, their idea is that they'll take advantage of the fact that floating point numbers are so uncertain and actually be able to steal value off of them. Good morning, Gersvak. Sorry, I didn't notice you. Good morning, Ing. Good morning. Last meeting, everybody. So that's what we're talking about this week. Floating point numbers and why are they so weird on computers, and why do they make programmers so miserable because of being so uncertain. If you've never seen this problem, you will at some point. You'll think that you have some value that's 1.99, and yet on the computer it looks like 1.98888888889. And it can happen very easily that what you thought was a precise floating point value is actually not as precise as you thought. Okay, anyway, so let's go look at what we have going on this week, which hopefully is a low-stress week for everybody. The programming project has a whole bunch of steps, but they're all pretty repetitive and similar, so it shouldn't be too difficult. But let's walk through the final week's module. So like most classes are supposed to do this at Butte this week. We're just supposed to run normal instruction. That doesn't mean you can't give a test, but for us it means we're having a normal week with no more projects, just one more lab. Okay, so we'll start with talking about how, what are the standards? How have engineers figured out how to represent floating point numbers on computers? And I'll kind of give you some examples on pencil and paper as to how those work. Then we'll do a little bit of programming to see how does the x86 processor actually allow for floating point arithmetic. And so that's the goals of the week. How does floating point work in binary, and then how does it work in x86 arithmetic? And what you should come away with is an understanding that floating point values they can very easily lose information, become not precise, just by the way they're stored in binary. I'm going to pop open a couple of the readings so that I can come back to those. So think it will be handy to have introduction to floating point arithmetic. It will be handy to have this IEEE 754 page, and it will be handy to have this. Actually, I'm just going to open all of them so I can come back to them. We will do binary to decimal, decimal to binary, and then a converter program. All right, so I've opened all the readings just so I can go walk through them when it suits me to do so. Same homework as always, based on the readings, 10 questions. Some of you are kind of in bonus stage, but remember that Canvas is going to drop your lowest 2 discussion grades, your lowest 2 homework grades, and your lowest 2 lab grades. So it may be worth it to do this week's lecture, homework, and lab so that you can erase something that was a lower grade. So Canvas will keep the highest 15 of those points, and then also the 2 projects. Let me open the lab. And then finish stepping through this, and then we'll look at how do floating point numbers work in binary. So the discussion this week is just because I like the routine of it. I don't like to have you wondering, is this a week where we do discussion or not? So we just do them every week. But it's really just, hold on. Get this off of here. Okay. The discussion is really just one last wish ourselves a great semester kind of thing, and know that we were all there together all the way to the end. So good job. And then the reminders page. So I should have put the usual things. In fact, I'm going to go do that. We have the usual things. I don't know why I didn't put them, but let me go put the reminders for this week. And then we'll get going. And then I'll bold that. Bold it more. Okay, there we go. So there are reminders because we do have the regular assignments this week. Okay, so let's talk about floating point numbers. So I'm going to go find the Wikipedia page. So we'll just start with the basic information. So IEEE is an international society of engineers. So they're a professional organization, and they publish journals for engineers. They have job banks. They support research for engineers. But one of the things that they also do is they define what are called technical standards. And technical standards are really just a solution to a problem that engineers as a group have come up with and agreed upon as a good way to solve the problem. So we have lots of standards in our line of work that we deal with. If you ever go into networking, there's lots of standards there. If you've ever looked at a web page, there's standards from other professional bodies about what the tags that structure a web page mean. So IEEE 754 is a particular technical standard that has been published by the IEEE Engineering Society. The nice thing about standards is that if all of us in the computing business, for example, use the same standards, then our hardware and our software become a lot more interoperable. So we love standards in our business. So this particular standard is a definition of how you can store floating point values in binary. The nice thing for us in computer science and computer engineering is that all of the processor designers and manufacturers, if they do floating point, they use this standard. So if you understand how 754 defines how floating point values are stored in binary, then that's likely to be the way that you encounter it in your computing work. Very often you don't care. If you work on the software side, you don't really care other than how does your language let you do floating point values. If you're a computer engineer, then you definitely care about this because this standard is what almost everyone uses when they design the circuits to do arithmetic on floating point numbers. Okay, so it's pretty scary looking if you read down through here. This table has some interesting information in it. We're only going to do one kind of this just so you can get a feel for it. But you'll notice that the standard defines several different sizes of floating point values. So there's a 16-bit definition, which I have never seen in a programming language. There's a 32-bit, and that's very common. So in C++, as an example, the float data type follows the IEEE 754 standard. In HLA, we call that real 32. The 64-bit standard definition, that is a double in C++. In HLA, that is a real 64. Anyway, so these are sort of the major definitions, the different sizes. And as you get more bits, just like with integers, as you get more bits, you get more precision possible. But even with 256 bits of precision, you still eventually run out. Imagine pi as an example. You can't represent pi in a 256-bit standard without giving up data because pi goes forever. So that's just an example. Anyway, if we scroll down here, we'll see this picture, which I'm about to use. So this is how the standard actually kind of starts. How many bits are we going to use to store a piece of information, and what are the bits going to mean? So this is the 32-bit standard, which is the one that we're going to play around with a little bit. So you'll notice that the 2 to the 31st bit, the most significant bit, that's simply the sign bit, and thankfully that's true. It's that simple. So if that's a 0 there, then the floating point value is positive. If it's a 1, the floating point value is negative. All the other bits are a little bit confusing. So the green ones, that's 8 bits worth. Those are called the exponent, and those are related to the sort of engineering trick that we use to put floating point in binary. It's actually pretty neat, but it's also crazy complicated. So those are called the exponent, and they are part of the sort of engineering and mathematical magic that we use to represent floating point values in binary. And then the last 23 bits are called the fraction or the mantissa, you'll often see, M-A-N-T-I-S-S-A. The fraction or the mantissa, and that's kind of the actual value that's being stored. So the fraction or the mantissa, 23 bits, is the value being stored. The 8 bits of exponent are a sort of bit of mathematical and engineering wizardry to make this work in binary, and then the sign bit is literally just positive or negative. So pretty crazy how that works. The other thing I'm going to show you before I do pencil and paper, we're going to do the 32-bit format, which we just saw a picture of. That's the single precision format. We just saw that there were 23 bits, even though this says 24, so I'll show you there's a little bit of a trick there. There's sort of an extra bit that we imagine to be in place. But what's important for us is this value right here. The exponent bias. So we need the exponent bias for doing the arithmetic. So I'm going to start writing on paper and do an example or two. What this is based on, by the way, is these tutorials that are linked in your reading that walk you through the process. It's harder than it looks unless you're really strong at math. it's difficult. So you don't have to do these problems, but I want you to sort of see how quickly floating point values sort of fail to be represented in binary. So what I'm about to do on pencil and paper is based on this example, and then maybe we'll do one other if we have time. So let me switch to camera. Okay, so here's what you need to know to do one of these problems. You need to know the bias. Well, you need to know how many bits, what number of bits you're using in terms of the standard. So we're going to do the 32-bit standard, which is called the single precision standard. We also need to know the exponent bias, which is 127. Where that number came from is the standard. So I didn't have to compute 127. I just looked at IEEE 754 32-bit standard, and it tells me that the exponent bias is 127. So once I pick 32 bits, then I know from IEEE 754 the rest of the information that I actually need. I need to know the exponent bias, and the standard tells me it's 127. I need to know the bit structure. So I have 1 bit of sine. I have 8 bits. If I get this right, 2, 3, 4, 5, 6, 7, 8. 8 bits of exponent. I'm just going to dot that part. I need 23 bits of fraction, sometimes also referred to as mantissa, which I just happen to like that word. 23 bits. So once I have read the IEEE 754 standard and I have decided that I'm going to use the 32-bit standard, then the rest of the information about how it works is provided to me by the standard. The bias, which is 127, the fact that there is 1 bit of sine, the fact that there are 8 bits of exponent, and the fact that there are 23 bits of fraction or mantissa, which add up to 32 bits in total. Now the thing that you don't see is what I call the mystery bit. Because it's a mystery to me how they figured this out. Not included in those 32 bits is the mystery bit. And you'll see in a second when we work through a problem how the mystery bit works. It's not included in the 32, but it's there, and it's kind of assumed to be right on the front of the fraction. So that part is kind of funky, but it's just the way that the standard is defined to work. So if you take a number, so let's just take one. It doesn't really matter. Let's try just something weird. Like 0.074, which looks like a totally simple thing, but the binary of that is not so simple, except for the sine bit. So that's the one part that comes easy to us. Is the sine bit for this value. Since it's not negative, the sine bit is 0. Thank goodness that's easy. Okay, now we get to the exponent and the mystery bit. So here's the way this works. We have to take this 0.74, divide it by 2 to some power, to get 1 point something. So this is kind of weird, but we have to do some magic here, some mathematical magic, to convert this 0.074 into 1 point something. And the reason why we have to do the 1 point something is because of the mystery bit. We need to take our actual value and make it look like 1 point something. And then from this process, we will get the exponent. So here we go. So the thing here is to understand a little bit of the math. The lab is not this. The lab is just a little bit of simple code. So yeah, Captain Price said, "Are we going to have to do this kind of stuff in the lab?" You're not. I'm the only person who's gonna do this work. You just have to do a little bit of coding, floating point stuff. So this, I just want you to see how it works so that you have the insight, but you're not going to do this handwork. Okay, so we have to get from 0.074 to 1 point something by dividing by 2 to some power. Now the trick is dividing this by 2 is going to make it smaller. So we're actually going to have to divide it by negative powers, which is the same as multiplying it by that. So if we were to divide it by 2 to the negative first, that would be the same thing as multiplying it by 2, which would give us 1, 4, 8. That's if we were to divide it by 2 to the negative first. 2 to the negative first is the same thing as multiplying this by 2. So, not good enough yet. I need 1 point something. But is this going to work out the way I want it? Did I do this right? 14, 2, 8, 14? Yeah, I did do that right. Okay. So 2 to the negative first didn't work. What about 2 to the negative second, which is the same thing as times 4. So if we do it times 4, we get, not 4, 16. So 4 times 4 is 16. 29. 2. So that's not quite there yet. So I'm going to keep going just to show you that, like, it's amazing that processors even do this, but they do. So let's try it by divided by 2 to the negative third, which is multiplied by 8. So that's 32, 56, 59. Not there yet. So those don't work. We haven't found this exponent yet. If I'm doing the math wrong, someone please correct me. Let's try 16. I'm going to cheat and use a calculator, by the way. So I need 0.074 times 16. Okay, so 0.074 divided by 2 to the negative 4 is the same thing as 0.074 times 2 to the 16th, which is 1.184. 184, hooray! We found this exponent that made this number be 1.184. That's just the way the standard works. So hopefully you at least kind of followed along. These are hard. Anyway, we found an exponent value. When we take our original value, divide it by 2 to that power, negative 4, we get 1 point something, 1.184. So the mystery bit actually sort of eliminates the need for us to worry about the 1 point, and we end up only having to worry about storing the 0.184. How they work this out, that's just the magic of engineers, particularly computer ones who are good at math. Okay, so we have this exponent, which we need to get in here. So once you have the exponent, you add your bias. So negative 4 plus 127 is 123. So we get an exponent of 123 from all that work. Isn't that crazy? Then we just store that. Let's see, that's 1, 2, 4, 8, 16, 32, 64, 128. So the exponent is going to be 64. What's 123 minus 64? Well, let's say 122 minus 64. My brain is not being friendly to this. 59, so 58. So I do have a 32 out of 58 is 26. So I have a 16, which leaves 10. So I have an 8, which leaves 2. So there's the exponent. That's simply 123 in binary. So we have positive number. We have the exponent, which is by far the hardest part to work out. And it's based on the way those engineers at IEEE figured out how to solve this problem. And basically convert a floating point value into something that could be stored on a computer in binary. So this is the value. This is the actual value that we're trying to store. So we had to go through this whole process to get this exponent that we then apply the bias to that we can then store in binary. So the rest of it you'll understand. Now we have to render the fraction off this 0.184. So the 1 part, that disappears with the mystery bit. So the only thing that has to actually be stored is 0.184. So let's do that so you can see how that works. Okay, so we have the mantissa. Sorry, I hit a lump in the paper. So 1, 2, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22. 23. Okay, so here we have the fraction or the mantissa. And we need to store 0.184 in it. All right, so how does this part work? For this part, you kind of go binary backwards. So this first bit is 2 to the negative 1. And then we just work our way backwards. 2 to the negative 2, 2 to the negative 3, and we can get all the way up to 2 to the negative 22nd. So now we just reduce this number into binary. So 2 to the negative 1 is 1/2, which is 0.5. So there's no 0.5s in here, so that's a 0. The next one is 0.25. There's no 0.25s in here, so that's a 0. The next one is 0.1. What is it? Is it just 0.125? Yeah, 0.125. That's 2 to the negative 3rd, which is 1/8. 0.125. We do have a 1/8. I'll keep going for a while just to show you how miserable this is. So the computer is still going, so it puts a 1 there. The next one after that is 0.0625. That's too big. After that is 0.03125. That one we can take. Something feels weird about that. 625, no, 0.03. Yeah, no, this is okay, I think. If I mess up, you should still get the idea. 5, 7, 7, 2. What I want you to see here is what's likely to happen. And this will be actually, okay, so now we get a 0.0. This is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4, 2 to the negative 5, 2 to the negative 6 is 0.01, 5, 6, 2, 5. We can do that. 1, 5, 6, 2, 5, 5, 2, 1, 2, 1, 0. So I don't know if you can see what's likely to happen here on something that's so tame as 0.074. Um, so this is your one lecture question is, what does it look like is going to happen as I work toward the end of these bits? Like right now, if I were to make the rest of these zeros, I'm actually losing information. I still have this much information that's not been represented in binary. And it's just going to keep getting more and more miserable. So 0, 0, 7, 8, 1, 2, 5. That one I can fit, so I can put that one in. But does anyone see where this goes? Well, I will tell you because I think everyone's a little bit stumped on this one. Where this probably goes is I'm going to keep whittling down this number little bit by little bit by little bit, and it's going to get tinier and tinier and tinier. There you go. So Tyler's got it. This is going to get what feels like infinitely smaller and smaller and smaller without ever actually reaching 0, which means that we're going to get down to 2 to the negative 22nd. And we're going to lose information. It's going to be a tiny amount of information, but we're going to lose information. So this 32-bit format, did you notice 0.074, how simple that seems? And yet, there's a good chance that when we try to store that value on a computer, some of the data gets lost. Crazy how that works. So you don't have to do any problems like this. That's not the lab, but I wanted you to at least get a sense, have seen once how this system works, and how easily you can lose information off of it. That's all I'm going to do. But you can imagine, like with 64-bit, these go way, 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 way tinier, but still, there's a good chance that this will just go on to infinity, as Tyler pointed out, never actually reaching 0, no matter how many bits you try to store it with. So those of us who work in programming and high-level languages, we have to be aware of this problem because it very easily can be true that floating point values actually lose something when you try to store them. Which is, I favor integers because I know with integers, I know the limits of an integer, so I know, and I will be able to detect if there's a problem like this. Anyway, quite crazy, isn't it? How that all works. Okay, so if you're interested, that's right. So Tyler makes a good closing statement about the point of all this, is that you can have a value, a floating point value you're trying to store, but the way that the computer is designed to store it, you may lose some of its value, some of its accuracy. It's tiny, tiny, tiny amounts, but if you are doing something like, say, working with a banking system that deals in trillions of dollars, that could add up over time. So from the software end, we have to come up with solutions to try to not have that happen, even though we know that the hardware is likely to do it, to lose accuracy. Pretty crazy. So floating point, pretty rough to deal with, and we should all be appreciative when a programming language or library figures out ways to compensate for that and make it so that we don't feel like we're losing information. So anyway, that was drawn from this tutorial. Okay, you can see there is also going the other direction. I'm not going to do it because I think you sort of get the point. But you can go from the other direction. If you're given the bits, how do you turn it into? Well, you have to get the fractional part worked out, 2 to the negative first, 2 to the negative second, 2 to the negative cube, and so on. So you get the fractional part, and then you attach that to a 1 dot something, the mystery bit. Then you take this exponent and you reverse the bias, so you subtract the bias going the other direction, and then you multiply your exponent by 2 to some power based on the exponent, and then you apply positive or negative. Anyway, that little tutorial does a walkthrough if you find those things intriguing. If you're a computer engineer, it might be worth your while to look into this if you're presently interested, but you probably will see it again. Okay, so there's the 2 tutorials. I also linked to this calculator just because it's kind of neat. So there may be questions on this on the homework, I don't remember, but if there are questions that ask you to convert things, use this calculator that's linked on the readings. You're not expected to handwork those problems, you're just expected to compute them and just kind of consider what it is that you're looking at. Notice, by the way, here they call the fraction a mantissa. Okay, so that's why that's there, so that you can use this calculator if on the homework it asks you to do any conversions. Then just punch them in here. That kind of stuff. If I make this smaller, anyway, there you go. So that's what this week's all about. Now, from the processor side of things, I want to show you how it works on x86. So on the processor side, we have this exercise just so you have some sense of how x86 processors manage this. The way they manage this, by the way, is they have a completely separate unit called the floating point unit that does its own operations completely separately from the rest of the processor. So this is pretty common in the processor world. If you have sort of a general purpose CPU, that it may either have or not have a floating point unit. Not all processors do, by the way, because not every application of a processor needs one. But if your processor is an x86 processor, then it has a floating point unit and it handles all of its operations completely separately from the integer operations. It has its own stack, it has its own instructions, completely separate. So that's what we're going to explore in the code, just so you can see how that works. And I'll get you started on a couple and then leave you to it after that. So let me copy these, and then I'm going to go switch the view and switch over to my virtual machine. And it may blow up a little, so I'll have to adjust. Yeah. Okay. By the way, I just noticed a bug in this assignment, so if you'd already seen it, this get float section, it had a numbered item in it. I took it off because that was, I didn't want that there. So if you already did it, no harm, but I did just make this update before I started, before I came on to Twitch this morning. I got rid of that number one and left you with that number one that was already there. Okay, so I'm gonna, well, I should have gone for the documentation first so we can see. So, but let's just see what's going on in here. So we have two inputs. Notice they are real 32s. So that is the HLA data type for the IEEE 754 32-bit floating point type. Or single precision is what IEEE calls it. Single precision floating point type. So these two variables are being stored on the computer in its floating point unit in that weird format. I don't even know how you begin to design a circuit to do that, but some of you are computer engineers, I think, so someday you probably will. Okay, so there's one change. Notice we're doing get F instead of get float. Instead of get I32, get U8, all that stuff. So we're doing get F, and then there doesn't seem to be any register. So let's go look and see what get F does. So I'm going to have to do a little bit of back and forth on the screen, but let me bring up my browser and let's go back. Oh wait, I already brought up the readings. So this is in the real arithmetic. If you do Control F, I'm going to do get F, and I'm going to find it. Okay, so I did a find in this reading that's linked on your readings page. The get F function reads a floating point value from the standard input device. It leaves the converted value in the top of the floating point stack. So this is in some ways different from what we're accustomed to. We're accustomed to things being deposited in the integer registers, but we're no longer dealing with integers, we're dealing with floats. So in the world of x86 floating point numbers and arithmetic, everything is done on a stack. So there's no registers for this, it's a stack. It's the same kind of stack that you're used to from the other side of the processor. So push and pop. So what this thing does is it reads in a floating point value and it pushes it onto the stack. That's where it leaves it, on the top of the stack. Technically the top of the floating point stack is referenced as ST0, but we don't actually need that information. So I just wanted to show you that. It doesn't go in a register, the library pushes it onto the top of the floating point stack. Kind of interesting. So let's go back and look at some other implications in code. So I'm going to scroll way to the bottom here first and show you where these are being used. So there's the get float, and that's going to, when it's done, have left a value on the top of the floating point stack. So this next instruction pops the floating point stack. So float, and then basically stack pop. So in x86, the instructions that deal with the floating point unit, probably all of them, but certainly at least most of them start with an F. So we're talking about a floating point operation here. This is the top of the floating point stack. And what it does is it pops the value off the top and places it in memory. So get float puts it in the stack, and then we pop it off the top of the stack and into our variable. Then we do the same thing for the second float. Get float pushes it onto the stack, and then we pop it off the stack into a variable. And then we start calling procedures. So stack, everything's on a stack. So let's look and see what happens on add numbers, which has already been implemented for you. So it takes two real 32s and does what with them? By the way, notice it has a local variable. So this is a local variable called sum. So this FLD, that pushes a value, that loads a value onto the top of the floating point stack. So num1 goes onto the top of the floating point stack. Then we float again, so we push num2 on the top of the stack, which means that num1 goes on the stack and then num2 goes on top of that. So the top two values are num1 and num2 on top of it in the floating point stack. Then this faddp. So let's see what that does by looking at the documentation. Sorry for the flipping back and forth, but let's look at faddp, which is probably, let's see if it's in here. It is, okay. So faddp, I just did a control F to find it. Okay, so the faddp instruction, we're not using it with two operands. We are using it without any operands. Does it talk about that? Where's the not? We want this one. Okay, the first two forms are equivalent. That's what, okay, so it's this first sentence. The first two forms are equivalent. They pop the values on the top of the stack, add them, and push their sum back onto the stack. So we could have said fadd, but I like the fadd and push, just it's a reminder that that's what it does. So what does fadd and push do? It takes number one, or it takes number two off the top, takes number one off then the top, adds them together, pushes the result back on the stack. So that's what it does. Which also is just kind of neat that it does that. Dock camera, no. VirtualBox. Okay, so what's happened here is push num1 on the stack, push num2 on the stack, add the top two values off the floating point stack, which is these two, and push the result back onto the stack. So what this one does is it pops that result that's now on top into our sum variable, and then we use some of HLA's trickery to print it. I love this. I love this. I wish every language did this, but HLA has a special printing syntax for floating point values, for reals, which is awesome. So we take num1, we give it a field of 10 characters wide, which just means it'll have some extra spaces probably, and then we say we want to print it to 3 decimal places. Then space plus space, then we take number 2 in a field 10 wide to 3 decimal places, and then sum in a field. So let me see if this will compile so you can see what that's supposed to look like. Hopefully it will compile. Okay, so here's that output line. So what my instructions have done is said, put this value into a 10 character width field. So that's why there's empty ones, is because there wasn't enough to fill 10 characters, but that's, and notice that by default it's right aligning it. It did the decimal places to 3, pads with zeros as needed, and then here's the second one in a 10 width field, and then here's the result in a 10 width field. So that's what that weird stuff means. Then there's also obviously some documentation there. Okay, so let's do one together, and then I think you can be done with me. So we'll do so this last one, we'll do that one together too. Okay, let's do this one together just to make sure that we have the routine down. So, and I'll ask chat to help. So what's the instruction to do this number 1 thing here? Chat? You don't need to worry about the semicolon part, unless you want. Should I scroll up so you can see the bits above? There's the bits above. Okay, so we want this for line 71. There we go. So we'll fload num1. So that pushes num1 onto the floating point stack. Yep. Oh, and Tyler, it's actually, I think HLA is case insensitive. It accepts the instructions in all upper letters, maybe. Actually, I'm not sure about that. It might, though. Anyway, okay. So what about for getting number 2? So now number 1's on the floating point stack. And remember, the floating point unit's kind of its own separate thing from all the other stuff we've done. Okay, so what's the, for the second instruction? Fload num2, good one, Tyler. Fload num2. Now this kind of tells you what happens next, but you'll find it in the readings, but you can probably kind of guess based on the add example on line 56 what this one's probably going to look like. Good one, Ursula. So F sub P. So that one is going to automatically grab the first two items, pop them off the top of the stack, subtract one from the other, and then deposit the result onto the stack. Okay, so after that instruction's run, now we have the answer on the top of the stack. So now we need an instruction to get the answer off the stack and into our diff variable. Yep, so we will pop the floating point stack, the top of it, into our diff variable. So now we have the answer from F sub P in our diff variable, and now we can do crazy awesome HLA outputs. So we'll take num1, we'll put it in a 10 wide field. You can experiment with that if you want to. We will do 3 points after the decimal. Then we will say minus. Then we will do num2 in the same way. We'll say a field of 10. That's just a guess, a field of 10. In this case, it depends on the numbers that they type in. It actually might not be enough if they put a giant number in. 3, and then equals, and then we'll do diff in the same way. So field of 10 wide, 3 decimal points past the decimal place, and then a new line character. So there's the minus. Let's see if we did those in the right order, by the way. Okay, making sure you can still see what I see. Let's do 1.23, 0.5. Okay, so those are all working as expected. So there's num1. So notice it's the thing on bottom that subtracts, the thing on top is subtracted out of it. So that's what we expected. Okay, so you'll know how to do multiply. You'll know how to do divide. Remember on divide, by the way, this is floating point. So when you're doing floating point division, there's no such, you don't have the problem of quotient and remainder because it's floating point. So the answer is the answer. So in floating point, the quotient is everything, right? It'll be 1.2783 or whatever it is. But there's no concept of remainder with floating point because it already accounts for that in the way the numbers work. All right, so divide you can do, so square root. I'll go show you where to find it, but one of the way I would do it is I would go in, these are the book readings, so one of the book readings goes here, so I would Control F to search and look for square or root and see if there's anything in this section of the reading that says square root. Aha! I see one. Square root. But we can probably find square root does not allow any operands. It computes the square root of the value on top of the stack. So before you run square root, you need to make sure that the value you want the square root of is on top of the stack. Which it already is. So if I want the square root of num1, it's already on the top of the stack. So then I fire off the proper square root function, and then I notice that the top of the stack is being popped into my square root local variable so that it can be printed out. So I think I just showed you that, but it also showed you how to find it for yourself. So do keyword searching in the readings for square or root or square space root. if you didn't get that just now. Okay, that's it. I think this lab should go easy. I hope that it goes easy for everybody. Remember, on the homework, you're not asked to hand work any of those problems. It's just answers. So what I recommend is that you bring up the calculator that's linked into the readings. So if you go back to the readings, you want this converter up before you do the homework. But notice what I did when I started is I just opened up all of them. But this converter will help you with the problems on the homework that ask you, how do you convert negative 3.2? Or what is the binary of negative 3.2? We'll use the converter to do that. Right? You just put in a number. And then you get the binary. So here's the binary. Or you can actually see it with the check marks. See? So I can make it positive, negative. Anyway, so that's the idea on the homework. Use the converter from the reading. You don't have to handwork any of the problems. I just want you to sort of see and think about how those work. The main goal being that you understand that floating point is just really weird, and there's a high probability when you're working with floating point numbers on a computer that you are losing information, that you're losing accuracy or precision just based on the way the binary for floating point system works. Okay. Oh, did I not switch the view? Oh, sorry, I didn't switch the view. So I'll repeat that. So anyway, before you do the homework, so you'll come here first, goals for the week. The second one will be what the readings are, and of course the homeworks are based on the readings. Just open all of these things. Particularly for the problems that want you to do conversions, use this converter. So open this converter, and if it asks you to do a conversion, use the converter. So if it's asking you to convert binary, you can type it in here in binary, or you can click the binary. If it's asking you to convert decimal, then you can type in the decimal here. And then you press enter and it does the conversion and shows you what it looks like in binary. By the way, did you notice 3.14? That last one's ticked off, which probably means that 3.14. Yep, look, value actually stored. It's not quite precise. So it's an interesting experiment. Okay, hopefully that's everything you need to have a run up to the end of the semester. I'll get the projects graded as soon as I can. It'll be this week. And anyway, otherwise, thanks for a great semester. If you need anything before the last due dates this Sunday, please just let me know by Piazza or inbox and I'll answer. Thank you, Gersbuck. Have a good day as well. Appreciate it. Captain Price, have a good day too. Thanks. Tyler, thanks. Whoever else is here. Oh, actually, he was here. All right, everybody have a great day. You won't see me for this class anymore, but you can get in touch with me through Canvas. So if you have any questions or issues, please just do that. Or use Piazza if you want to interact with me and other people in the class. All right, have a great week. Thanks for a great semester. And good luck for whatever it is that you're headed next. I hope you do well.